some history. Feedforward neural language model. So we use word embedding as a feature, and then you concatenate the embedding together to become a feature vector. Okay? So once you have the feature vector, you can use it as a classifier to predict the next word. Yeah, so far so good. So it combines all of the ideas that we know. It combines the idea of word embedding. When we train word embedding, we try to predict the word that's in the middle, right? Now we try to predict the words that's on the right, the word that you haven't seen. And to take the feature, to use the features, you use embeddings as features. And it combines the idea, that idea of embedding with feedforward neural net, which we just saw as well, so that it can make a better prediction. And yeah, you can add as many hidden layers as you want. A pictorial representation of the pictorial representation is something like this. So we've got, these are the words. Suppose you got a trigram model, 4-gram model. So you look back 3 words. And for each word that's in the context, you convert it into a word embedding. So this is a lookup, okay? So look it up in the table. You concatenate it together. You concatenate these together and connect it to the hidden layer. And the hidden layer is connected to output layer. So the output layer is a softmax over the vocabulary. So these are the techniques that we have seen already. So they all come together now. Yeah, and to train this, you use backpropagation, the normal thing that we just saw. So when you train, this language model, you adjust the weight between the hidden layers and the input layers. That's one, and you also adjust the word embeddings that are used in that context as well. So if these 3 words appear in your context, then you update the word embeddings for those 2. So they all updated at the same time. So first you pre-train the word embedding, and then you fine-tune it more when you train the language model. Yeah? Or you don't have to. You can just train everything all at the same time. You don't have to pre-train the embedding too. So there are choices. Okay, cool. So the results are actually great from 2003. So these are all the parameters that they look at. So on this column is n is what's the n gram. You look back how many words back, so that you can compare with Kineso9. Kineso9 back off. That's the LM that we learned before, the n-gram LM. Okay. And H is the size of the hidden layer, so it's 50. And M, I believe, is the size of the embedding, so 60, so small. 2003, you know, we don't have much computer. 2003, are you born yet? 2003? No. Oh my God. Okay, that kills me. Really? This is before you were born. Darn. No. Okay, so yeah, on these columns, the value for train, validation, and test, these are perplexity. Just to review, perplexity, the lower, the better. Okay, it's an evaluation metric for language model. So from these experiments, you can see that for the most part, if you do it right, if you add enough hidden layers and you train it enough, you get the perplexity that's much lower than the best n-gram model that we have seen. So this is quite promising because now you use embeddings and you hope that it will work, and it did. Okay. So feedforward, and then nothing happened for a long time. And then 2016, we got RNN. RNN It's actually a very old idea, but people bring it back now that we have better computer. So the idea is to use RNN so that so you can go back as far as you want. If you look at the equation, for example, if the first word is Peter and the next word should be Griffin, here's how you set that up. So you have the weight, WH, and the input into this node is X1, which is the embedding of the word Peter. And the blue thing, since this is the first word in the sentence, we will give it this H0 thing as the initial case. Okay, multiply that with W so that it got. I think this is wrong. This should be longer. Okay, so H1, this is a hidden layer. Okay, so what the hidden layer does is that it tries to combine the embedding and this guy, which is the context vector. We will call this a context vector. And once you got H1, then you do your usual softmax thing, okay? So that Y1 is a probability distribution over the vocabulary. Again, things that we have seen already. Okay, Y2 is kind of the same, but the input to the hidden layers consists of two things. Consists of the word embedding for Griffin and H1. H1 is the hidden layer from the previous time step. Okay, from the previous time step from word number 1 right here. So you concatenate that, multiply it with some weight matrix, add a bias vector to it, hyperbolic tangent, some activation function. It can be ReLU, it can be hyperbolic tangent, and you got H2, and then you softmax that. No, you connect it to a classifier, multiply with the weight matrix, add bias vector to it, and then softmax that. And then you do it again and again. An important observation here is that WH is the same regardless of the time steps, and BH is also the same regardless of the time step. WY as well, the thing that converts H at various time steps into the probability distribution, also the same. So we reuse the same parameter set for all time steps. Okay, and you keep doing all of that. So at this point, when you use it, then you try to predict the next word. What is the next word? YT, and YT is a probability distribution vector. So this is a large matrix multiplication, which you have to do. You cannot do negative sampling here. There's no way around it. Okay, cool. All right. And to train it, you do the normal. We'll talk about backpropagation later for RNN. So when this technical term that you need to use, since RNN, when you try to predict the next word, you need to know, say for example, lives, and then you try to predict the next word, right? Then you need to know the embedding of the word that you predict out. In this case, suppose you actually sample and get the word in, then you need the embedding for the word in as an input for the next time step, right? But during training, we do this thing called teacher forcing. That means you don't make the model generate anything during training because you use the actual words that occur in the training set. Okay, so it doesn't generate at all. So you compute YT so that you can compute loss, but you don't use the probability to generate yet during training. Okay, it's for computing loss. And this is called teacher forcing because you use the actual words that are occurring, not the word that's predicted by the model, okay, during training. So all the parameters, there's so few actually, so few parameters because you get all the embeddings, right? And the parameters that are not embeddings are the weights that are in the hidden layer. So this rectangle, the bias, and the weight at the classifier where you try to predict the vocabulary, and the bias for the vocabulary. So there are not a lot of parameters. All right. During inference time, that means when you actually need to use the model, then you need to process the hidden layer from left to right for each time step, from the first word to the next word to the next word. So suppose you have the context, Peter Griffin lives, it should try to predict the right probability like so, right? And from here, you would sample from this probability. What it meant by sample is that you toss a die and see which word you actually get based on this vocabulary. So in will have the highest probability of getting picked, but there's a chance that and can get picked as well because you get some non-zero probability here. So you also get something non-deterministic here. Okay? So during inference, that's what we do. We, from the probability distribution, we sample based on the probabilities. Once you've got that, then you can go ahead and look up in your model, in your embedding dictionary, what the embedding for in is like. And also to predict the next word, then you do the same thing. So you use this guy and this guy as an input, multiply by weight, blah, 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 and then softmax, blah, 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 then you get this, this probability distribution for the next word. Okay, so yeah, so suppose you get new, it's very possible, right? Although it's not very likely. Even like the most likely word is the, right? It's like 6% probability, it's not a lot. That's usually the case when you have a language model of sort. All right, suppose you get the word new because you sample based on this distribution. Then you do the same. You look up the word embedding for new using an input, and use the hidden layer that you use to predict new to form the new hidden activation for the next time step, and so on. All right. So another technical word that you need to know is that this is an auto regressive model. Auto means itself, right? Self, back to itself. And regressive, that means you make a prediction based on what you get from last time. Okay? Regressive, like regression, like linear regression. Okay? So in NLP context, if it's an autoregressive model, that means the prediction or the sample that you got from the previous time step is used as the context for the next time step. Time step mean word now, right? Next word, over. Okay, this is an auto-regressive model. All right, RNN-LM is a wonderful neural language model. So if you train RNN on Harry Potter, is this also before you were born? Harry Potter? Yes, it's before you were born. Have you read Harry Potter? Yes. Watch a movie, maybe one movie. Yes, it's a story about this wizard and try to blah blah. Class some classic now. If you haven't read it, you should read it. Okay, so if you train on it, then it will try to mimic what happened in your training text, right? So it learns the character's name, Hermione, Malfoy, Harry, right? And all the words, you can see that all the sentences are mostly grammatical and sounds very English-like. Okay? For example, he put his head back behind them and read groups as they cross a corner and flutter down to an ink lamp. Actually, it doesn't make much sense, actually. But it does sound like a bit of English. Okay, the bell rang. It was a lot cleaner down in London. Yeah, so it looks something like this. And if you train it on Shakespeare, I think this person is Shakespeare. So you get a playback. Okay, Shakespeare is a really famous playwright, and so you can see that the text that generated from it looks very different from when you train it with Harry Potter. So it will mimic the training set quite well. Silicon Valley, so if you train it on the screenwriting from this series, so you even get it in the series in a screenwriting format. So so it picked up the name of the characters, right, and then you get something like a dialogue back, which is great, which is awesome. All right. So from these, people use many kinds. Some use character RNN-LM, which is kind of nice because your vocabulary becomes so small. So you get 26 letters from the English alphabet. That's the small alphabet, and the capitalized alphabet. You get another 26, and you get some numbers. So your vocabulary size becomes very small. So you can train it quite fast. So if you train it on the word level, then your vocabulary become the vocabulary of the entire English language, right? So you get a vocab of 20,000, 30,000. That can be quite cumbersome. So character RNN, when people try, it worked really well. Although one word is 6, 7 characters, right? 5 characters. So it needs to know the dependency between it needs to learn the patterns, but beyond 5, 6, 7 characters, if it needs to output something like this. So to output something like this at the character level, what it means, the model output one character at a time, not a word, one character at a time, and it still makes sense. For example, if you want to generate COME, it has to look back at basically all of the characters. So if you want to use character n-gram language model, it will have to be like 30 character language model, because it has to look back so much. So and you can actually train character-based RNN language model, it is a proof that the model can learn really long-range dependency, really wide pattern beyond just like 10 characters, 20 characters. So it can learn such pattern in language, which is very important. Okay, so yeah, but people use both, and it's all. Oh, I have some example. So when you train RNN-LM on a character model, if you let it generate at many points during the training process, you can see that it kind of cute, because at 100 iterations, what do you get? Gibberish, right? And 300, you can still gibberish, but if you look at it from like 50 meters away, and you're like, that looks like English. But if you actually read it, it's not English, right? 500 iterations, you can see that it pick up words, right? That's word counter, his, one, that, wish. So like some of the function words that they see more often, the model already picked up. So you can see the evolution during training. Okay, this as well. So you can see that it's the same. Yeah, so it get better and better. 700, 1200, 2000. From 2000, you can see that it form almost English-like a sentence now. Okay, and the perplexity for RNN. So the first role is again n-gram language model. Perplexity is 60. It's actually not bad at all. But once we have RNN, it came down even more. Again, perplexity, the lower the better. Okay? All right. So what we saw, let me finish this then. What we saw though is that we don't need to specify n at all, right? For the feed-forward language model, we still have to say how many words you want to look back. For RNN, there's no need. If you look at the math, actually, if you look at the math for this guy, right? To compute this guy, it actually has some memory of the embedding of what happened before. All like way back in time, because it process one word at a time, right? To compute this, you need this embedding. You need this embedding, so it accumulates the context from left to right. That's what the math says anyway, right? And it worked out fine in real life. Okay? Mm-hmm. Oh, backprop. Oh, okay. Before we look at backprop again, I've got sample code, which is so that you have it, but it will take a while to train until it does something useful. Okay. New tab. And let me use the Colab Pro Plus so it can do something cool.
So you pay for Colab Pro?
I pay for Colab Pro, yes.
How often did you get like a more beefier GPU? Like those like.
How often? Almost all the time.
Like what is the GPU you get like most of the time?
I'll show you. I'll show you.
Because I heard like during the very early time of the when the Colab Pro first introduced, it's very hard for you to get like the B100.
That's right. That's right. Not the case anymore. You can use it all the time now, I think. I want to set that going so that when we're back from the break, we can see how well it works. It takes a while to train and a while to share permission. Okay, good. All right. Cool. So let's go through a code a bit. You load the data set. Again, tokenization stuff, convert the data, blah, 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 and train, okay? It's not super interesting, but oh, no. So, yeah. If you pay for it, you can choose like cool stuff.
So what is the reason would you take a T4 over A100?
I have no idea, actually.
Who will choose that?
Because I know what it is. I know what A100 is, so I'm gonna pick A100.
Why would you choose T4 over L4? Like who will choose it?
No idea. I know like A100 is like like a standard NVIDIA GPU chip, so I'm gonna go for that one.
Is the L4 faster than the A100? I think L4 is newer.
Can you ask ChatGPT for me and share with the class? I actually don't know. I'm gonna do that right now, but yeah. Okay. Don't use CPU to run it. Okay, I'm gonna run that. Cool. It's okay. All right. Okay, I'll let it train while we are doing something else. All right, backprop. Hope you still have backprop, on your camera or in your notes. This is a loss function when you want to train RNN, right? So the loss is the log probability of the next word given the context, right? So for this one, it's a log probability of student and so on, right? And then you sum it over all time steps. That's your loss function. So yeah, remember that one. So this is not super hard. I'm not gonna do the derivative and stuff for you because I already did that once, but it's quite similar. And to compute the gradient, that's a little tricky thing because it has to propagate back quite far, right? It has to propagate back all the way back to the first time step, because in order to predict the next word right here, this is your computation graph, right? So you need to compute the gradient between these, compute the gradient of this, compute the gradient of this, and compute the gradient of this, right? To get the partial of the loss with respect to the first time step. So this is what you end up doing, right? Since we have this computation graph, and we saw before that how we compute the gradient is that we propagate the gradient back, right? So we compute the partial of j with respect to h4, and partial of h4 with respect to h3, the partial of h3 with respect to h2, blah, 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 and then multiply that together. So we keep multiplying more and more until you get to the last time steps, and you give it the gradient with for each time step along the way. Okay, because then you need to update the weight here. Update the weight at this point, update the weight at this point. Okay, so after you see this, you can see that you ended up multiplying a bunch of gradient together, right? So when you look at the equation here, so this will go back in time. So we call this backpropagation through time. Backpropagation through time because it's right here, because you have to go back in time, okay, all the way to the first time step. And for each step, you compute this guy, the partial of ht with respect to h of t minus 1. Okay, and compute this is not super hard, right? For each time step, this chain rule, partial of ht with respect to z, we already know this, which is what? It's either 0 or 1, right? Because if it's a ReLU. And the partial of zt with respect to ht minus 1, this is the equation. So these two terms go away. They are constants, right? And what we end up with right here is just the weight, WH. So this is very easy to compute. So you end up with just this, WH. Okay, so this term becomes just WH. And so the pi thing, that's product, okay? Product through time. So you end up multiplying the weight with itself that many times. So it becomes the weight to the power of L, where L is the length of your sequence. So what happens if your weight is 0.1 and you raise to the power of 100 because your sequence might be 100? So you get how many zeros? 100 zeros. So the gradient for the last time step basically 0 because you multiply whatever thing by 0.01. So this is called vanishing gradient. So which means, so whatever error you make here would never influence the embedding at time step 1 because it vanishes over time because you keep multiplying W that many times and W is less than 1. So between usually in the decimal points. So this is how I show that there's a problem of vanishing gradient. Okay, that's an actual proof, but I'm not going to make you go through that. So by this proof, so to say, it's we know that the model will learn only local dependency. How local? We don't know that. Okay, it might be like 20 steps back, 30 steps back. Okay, so because of the math, it's clear that it's not going to be that effective. It will be limited. Is the model still training? It's still training. Okay, very good. Okay. All right, let's get back to this thing. Okay. The supervision. This is all fun. This. Okay. It from 2,000 steps, it knows some grammar now, and now it goes somewhere not great, and I hope it will come back at some point. It's a bunch of 911 now.
What?
This is story 911. Well, it will come back at some point. It will become a good model at some point. We cannot lose hope yet.
911 will come back.
Maybe the loss still going down, so maybe it will get good, but we'll come back to that. Oh yeah. Okay, so I hope from this equation you understand why this is a problem if we use propagation back through time. Okay, I already saw that. Yeah, I already said that. Okay. Okay, for the very same problem, if W is, say, 2, and then you propagate back the error, so you get 2 to the power of 50 to the power of 100, then it's going to explode. Then you end up multiplying your weight with the gradient. The gradient is like 200,000. That's definitely not good. Okay, so this would become a problem as well. So to train this W, you have to be within the same range so that it doesn't explode. And I don't think my thing exploded. It's still in the right range. So that's good. Okay. So gradient clipping. So if that happened, I think PyTorch also does that for you. It will clip the gradient. So suppose you get the gradient of 10,000, it will clip it to 2, so that it's within the range. So that's how we solve it. So this doesn't happen very much anymore, because we clip it down to like 1 or 2, so that you don't multiply something. You don't multiply your weight with 10,000, which is a big number. Oh yeah. It used to be a thing, not a thing anymore, but I'll just tell you that you can use RNN as a classifier as well. It's okay, it's not super effective thing, but you have this concept called the language head, the language model head. This become a language model, right? So when you want to turn this language model into a classifier, you can you use the last hidden layer and connect it to a classifier. Again, the same trick we saw before. We use the last time step, the hidden activation of the last time step, and connect to a classifier so that it gives you a label instead of the probability over the vocabulary. Okay. So we will come back to this idea next week when we use transformers to classify text. Okay, so this last thing, the feature that you use to use as a classifier, we call that language model head. Okay, head as in the head of a person. Okay, so you can do that, but we don't do much with RNN this way anymore. Or you can do it this way as well. This is actually more effective. You pull together all of the time steps by pooling elements, add them up. It doesn't make any sense, but it's cool. But this works much better because the gradient is tighter, which means the error from here, right? So you can see computation graph will go back here, right? Here, 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 and here. So the error that you get from the label is very close to all of the embeddings that you need to train. Compared to this one, right? To get the error to propagate back to this word, it have to multiply over W that many times. So the embedding for gradient hardly ever got, the embedding for Peter hardly ever got any gradient from the label. But if you set the computation graph this way, or you set up the model this way, the gradient from the label can flow very close to each word in each time step. So it doesn't matter how long your sentence is, it will receive the gradient a good amount. Okay? So when you see the diagram of the model, also think about it as a computation graph and how the error will flow back from the loss function. Okay, so we got exploding vanishing gradient. So RNN means can encode some long range dependencies, but it has some limitation to it. It cannot go that far back. Okay, because the problem is the hidden vector try to do two things all at once. If you look at the model, the hidden layer, the hidden actuation can want to do two things, right? It try to be a feature for predicting the next word. And it also acts as a memory cell. So it tries to memorize what happened from the left so that it can pass it on to the next time step. So it has to do two things at the same time. So that's also an observation that we make about this model so that we can have more fancy models. We'll train an LM. Okay, I think I show PyTorch. So what happened is, let me show you this one actually. So the code I already posted, I think. So first read raw data, tokenize it into word that based on your word embedding. Create the vocabulary. I think I already said that. The tokenizer class it's not in Keras anymore, but yeah, for PyTorch you need some mapping from word to index and index back to word, and you need one space for padding and one space for unknown word. Okay, so make a vocabulary for it, something like this. So we have a mapping between words, okay, between word and some symbol that you need to recognize. Convert string to indices based on the vocabulary that you just created. So instead of having these strings, you have a list of indices like this based on the vocab that you create. Okay. Padding, truncation. I just said I just talked about that at the beginning of class. So instead of 134, 16178, 56178, we pad it so that it's the same length. Okay. So you add 0 to the front. So then we get a data matrix, now become a matrix because the number of rows and the number of columns are the same, or not the same. Now it looks like a matrix now because it looks like a table, a full table, okay? Awesome. Oh, labels, where do we get the labels? The label should be itself, right? Because it tries to predict the next word, right? So the label for mai should be ru, right? The label for ru should be aroy. It should be like the next word over. So so we try to offset it so that it looks something like this. Okay, so we try to push it back one. Okay. So yeah, it should look something like this, right? And then the last word has nothing to predict to because it's already the last word. So now your X and your Y would have the same size now because we drop one, the last word out. Okay. Yeah. And so what you ended up doing is that you clip the back out because the last X, you don't have to predict anything anymore. It's already the last thing. So you get the actual X from the data. Okay, so you clip 4, 8, 10, 10 and out. And to get the label, you clip the front. So now that you can see that now it's more, now it's aligned, right? So 1 will have to predict 3, and 3 will have to predict 4, 5 we need to predict 6, 6 we have to predict 1, right? 5 predict 6, 6 predict 1, 1 predict 7, 1 predict 7, 7 predict 8, right? 7 predict 8. So, pre-processing. Again, not the sexiest thing in the world, but you know, needs to be done. And yeah, I give you the PyTorch code. And oh, all right. So I think I actually finished training tier 3 epochs. Not bad at all. And it took how long? It took 26 minutes. Not bad at all on the 800. And yeah, let's say this is not bad actually. If I say what should be the first few words? The little girl. A little girl found. Let's see what she found. A little girl found a big box. She was so excited to see the box and the key. She opened the door and saw a big shiny box. She was so excited. She's still excited. She opened the door and saw a big shiny, and it keep going on the same way. Okay, because it already forgot that it generate these things already. Okay, so yeah, so you can see that it's the amount of context that RNN could learn is actually not bad, right? It can generate 2 sentences that are kind of consistent. It knows that she here is makes sense, right? Because we talk about a girl before. So we have an RNN that can write something. can write something. Okay. And let's see if I do it 1 sentence at a time. What will you give me? So so let's say we want to keep it just 2 sentences. Let's go. She was so excited to see the box and the key. She opened the door and saw a big box. She opened the door and saw a big box. She opened the door and saw a big box. Not a great language model. I should have trained it a little more, but you get the idea. Okay? All right. Language model. Fancy RNN. I don't want to go through this at all. Okay. Then don't worry about a fancy RNN. Yeah. I'll make sure that it's not on the test. Because I want to talk about better things. Transformers. Let's talk about transformers. So from RNN, you can see that the problem with it is the long-range dependency, because in languages we need to model something that has a really wide context range. So fast forward to 2017. So RNN didn't stay for very long. So we learned from the previous model that n-gram is a great idea already, right? Because it learns about language, it encodes some of the knowledge inside. So n-gram is not a bad model. It's very quick to train, right? So it didn't take 25 minutes to train to get a lousy model, you can count a bunch of n-grams and it will do a decent thing. It's actually not a bad idea. But neural n-gram, it helps with the sparsity problem. So you can deal with the environment or the context where you haven't, the context that you haven't seen before. And once we move on to RNN-LM, I will remove this, not talk about that. It helps somewhat, but it has its own setback. The model is not set up right. It still has the vanishing gradient. There's other models in that same family that help fix the vanishing gradient, but it's still not a good model. So we have this thing called GPT. It's called stand for Generative Pre-trained Transformers. So the keyword here that we will focus on is transformers. Transformers are pre-trained to generate text, and that's awesome. And GPT is the best language model we got by far. I don't have to say that very much, I think. Everyone already knows. So transformer, it actually improves upon this architecture where you see that there's the relationship between each word is too loose, but in language you see many relations that go so far. So from paper 2016, they proposed this method called attention mechanism in 2016. So here's the architecture. It looks very much like what you see in RNN. So you have embeddings for each word that is in your context, and you pass it through some model, and at the end you get the embedding for the last word, and use the embedding for the last word to predict the next word using softmax. So that's what we know already, but today we will look at the inside of these blocks. So a transformer, or let's say GPT, it consists of many transformer block, and one transform. When you zoom into one block, you can see a common structure. That's a self-attention block. So self-attention, you take in a series of word embeddings, and it will do this self-attention operation, which we will talk about later. And the output of that is also a sequence of embeddings. Okay, so if you get 8 embeddings, you get back 8 embeddings. So that's why we say it's a sequence of embeddings, and you pass it into layer norm layer, and to the feedforward layer, and do layer norm layer again. But today we'll talk about self-attention only. Okay, and once you do all of these things, again you end up with 8 new embeddings, and you pass it on to next block. Okay, and the next block has the same structure, different parameters, and you do that many times. Okay, so that's the idea. But let's zoom in on self-attention and why it's a key to a good language model. So attention mechanism. So in general, it's a formula for computing word embedding by looking at all other words around it. Okay, so the idea is that you want to pay attention to different words, different amount. So here comes transformer. Okay, transformer. Here's how they think about a language. So if you have a sentence, a robot must obey orders given to it. Actually, to understand this sentence, a lot has to be going on. So for example, to understand the word it, you need to know that it refers to robot, right? So the meaning of it and robot should be quite similar. So, and you can see that the dependency is kind of far. So that's what it meant by long range dependency. So this is what RNN doesn't do so well, and attention mechanism try to fix this by make the connection between the two words tighter, okay? So that it doesn't have to multiply W 6 times, so that it can be connected. And look at the a meaning of a verb. A verb is kind of hard to understand alone. To understand the meaning of the verb, you need to know the subject and the object, right? So to understand the word obey, you need to connect together the embedding of robot, obey, orders as well. Okay, so orders is also is an object to obey, right? One more, given. This also very, very English. So given, where's the object? Orders, right? That's an indirect object, it. So to understand this word, you need to know indirect object and the direct object. So there are many relations between each word. So to be able to understand this sentence, you need to model these relationships, these dependencies. And this is what linguists have been looking for a long time already. When you study grammar or syntax, we look at relationship between words, right? For example, must obey, right? When you use the word must, it must be followed by a verb. So for example, you have this kind of relationship. So yeah, in linguistics, we study relationship between words already, and attention mechanism take advantage of this observation, okay? And to implement this idea, an easy thing is to use the weighted average. So that means to get the new embedding for the word in the sentence, let's say in the sentence, the dog ran, to understand the word the, it needs to know what is a determiner for, right? The is a determiner for dog, so it should give it more attention than the word ran. And to get a new embedding that is contextualized, as in it consider all of the dependencies for the word, you need some way to compute the attention between the word that you try to get the embedding for and all of the words in the sentence. Okay? So far so good? So that is the idea of attention. So you try to model dependencies between words in the sentence. So to do that, they come up with this really cool model. It's called self-attention. So self-attention in this model, for each word, we give it 3 sets of embeddings. It's called query vector, key vector, and the value vector. I give you the definitions right here, and I think they make no sense. So let's look at an example. So first, so I said the query vector is a vector that for the word that we want to compute the representation for. And in self-attention, we want to compute the word embedding for all of the words. Okay? All the words that you try to understand in the sentence. So for example, the dog ran, you want the embedding for the, you want the embedding for dog, you want the embedding for ran, that already pay attention to different words, different amount. So at the end, for self-attention, you want to convert all your words into the query vectors so that you can use it for computing attention. Okay? So key is the word that we want to know how much attention they want to give it. So for example, the should give the 0.5, dog 0.3, and ran 0.2. These are attention, okay? So attention become the weight of different words in the sentence. Not in the vocabulary, okay? In the sentence, just that one sentence. If that sentence has 7 words, we want to know how much attention to give to each of the 7 words, okay? not the vocabulary of 20,000 words, just that sentence, all right? And the value is the vector is that we want to compute the average for. So in this case, the blue vectors are the value vectors because those are the vectors that we use to construct the new embedding, which is contextualized. So query and key will be used to compute these things. If we use to compute attention, 0.5, 0.3, 0.2, okay? That's what we will use Q and K for. And the blue things are the V vectors. All right, let's look at an example, okay? So suppose you have this sentence again, a good robot must obey orders given it. You convert it into the Q, the query vector. To convert that, you first do the lookup, okay? Look it up just like what we did in Feedforward net. So for each word that is in this sentence, you look it up and turn it into the embedding, okay? Once you have that embedding, you multiply it with this WQ. WQ, this is a matrix that would convert. Okay, so whenever you see matrix multiplication, think about it as a conversion. It converts something into something. So WQ convert embeddings that are not contextualized into query vector, okay? And what is a query vector? A vector has to encode something. Here's what we think intuitively. The query vector, it represents what each word is like looking for. So for example, the word it should look for robot, right? It should look for what? A singular noun, for example. Or robot, to understand this word, it should look for the adjectives that are in front of it, for example. So intuitively, the query vectors encode these things that they are looking for, okay? So must as well, it might be looking for a verb that come after. So it should have what? It should have an infinitive form, for example, okay? But we don't know for sure though what query vectors actually like encode, but we believe it encode this kind of thing, encode like a question that it will ask each word. And how do you know that what would say yes to it? So for example, if Q3, if it actually does it this way, if it asks, are you an adjective that is in front of me, for example. So key is the answer. And we want to know if the answer match with the question or not, query, right? It matches to the question or not. So in this case, the same, when we want to convert the embeddings into the key vectors, you multiply, do I have no, I do not have it. So you multiply the embeddings, see, the same E1 right here, right? But you multiply with WK, which is another matrix that converts the embedding into a key vector. Okay, so to compute attention, you do dot product between query vector and the key vector. So the dot product between Q3 and K1 will indicate how well they match between this question and this key answer, if they go together or not. So for K2, Q3 and K2, they match well, right? Q3 is looking for like an adjective that's in front of itself, and K2 is an adjective, then it's kind of match. So it should pay more attention here. So when you do the dot product between Q3 and Q2, it should be high. All right. But Q3 and K3, if K3 encodes something like I am a singular noun object, then it should not match. Okay, so Q3.K3 should be small. Again, this is an intuition. it doesn't really work out nicely like this in real life, okay? All right. So this is self-attention. So like you try to figure out how much attention it should pay to the words around itself. And this is what you end up doing, okay? Because you want to ask the same question for every pair. How much attention should this word A pay to A or good or robot or must or obey or orders or given or it, okay? So you have to do all combinations of that product. So in real computation, you convert all the embeddings into query vectors, and you convert all the embeddings into the key vectors, and then you multiply them so that you get all the pairs, all the cosine similarity pairs. And you might get something like this. The bigger circle, the more attention. That means a higher cosine similarity. Okay, so you might reveal a pattern like this. So for example, given might want to pay more attention to robot. Robot might be what? Might be the object of the indirect object of the verb, right? Orders is direct object of it, so it should get a lot of attention as well. And it is also in an indirect object, but it's in a pronoun form. So you might get something like this, okay? So, so the point of query and key is to compute attention in this fashion. And what else? Now you get some score like this, right? Usually smaller numbers, not like this, okay? But I want it to be clear. So we want this to become weights. To turn any vectors to be weights, we softmax. We see it every week, right? So we softmax over the attention, the dot products that you make between Q8 and all of the Ks, 1 through 8. So you might get something like this, okay? So what is shown on this graph here is the attention. So attention will look like a probability distribution. So it will be between 0 and 1, and they will sum to 1. Okay, so these are the tricks that we have seen again and again. We rely on softmax like for everything. So at the end of the day, you end up with an attention matrix like so. So you could check for yourself that all the columns that you see in the attention matrix, they all sum to 1, and all of them are between 0 and 1. All the values are between 0 and 1. Yeah? So far so good? Yeah? All right. Moving on, we haven't got embeddings yet, right? We only know the attention. So we know this part, right? Now we have the attention. How much attention you need to give to it. But then we need to put the embeddings back together, right? Think of Transformers, the movie, you have different parts and they go into like a new thing, right? That's the metaphor they're going for, but it doesn't work, I think. It doesn't work at all. So what you end up doing here, though, suppose for the word obey, you already compute the attention it needs to give to different words in the sentence, right? So it should give more to orders and less so for must and robot, and all the others are 0. So to construct a new embedding for obey, you need value vectors for each word, and we're gonna weight each value vectors by the attention, like so. Okay. So once you weight each value vectors by the attention, then you can sum them up, like so. Okay. And once again, We do that for all of the words because we want a new embedding for all the words in the sentence. So at the end, you get e prime of 1, e prime sub 2, e prime sub 3. So this is the new embedding that are highly contextualized because it already pays attention to different words, different amount. The right amount because the model should do really well in figuring out the relationships between words. Okay, so this is a self-attention operation. One time, it takes what? It takes a sequence of embeddings, compute the attention matrix, and then construct a new series of a new sequence of embeddings based on the attention matrix that you just computed and the value vectors. That's self-attention. That's what changed the world, is this self-attention equation. Any question?
It's sort of like the dust at the center.
Yeah.
The information is in, but
It's in the air. Let's settle a little bit. Okay. Let me repeat myself one more time though. So first step, okay, you want to compute attention. Attention is what? Attention is like how much attention each word need to pay to which word, and it's represented in this matrix, right? Like this. So robot should pay attention to this amount, or A should pay attention to these words, this amount, okay? And to figure out the amount, you use the dot product between the query, which is the word that you want to compute the embedding for, and all of the words that are in the sentence. Okay? And you normalize it column-wise, so you get the weight, and the weight are the attention, okay? How much attention, how strong is the relationship, and reconstruct new embeddings by using the attention as the weight, and you add up the value vectors according to the attention. And do that for all the words. Okay? Cool. So, yeah, it's a lot of computation to do this one time. All right. That didn't seem to be the end. So why do it once when you can do it many times? So attention head, every large language model that we see now use multi-headed self-attention. So let's look at the picture. This is what it looks like. So we saw just now, right? So this is one doing self-attention one time. Self-attention operation convert a series of embeddings into another series of embeddings, right? Using attention, using self-attention. And the parameters for self-attention, one time, one head, is the WQ that convert the embeddings to the query vectors, and WK that convert the embeddings into the key vectors, and WV that convert the embeddings to the value vectors. Okay, so one head has three matrices, weight matrices, and here's the output. So in real use, we do that many times, 12 times, 21 times, I think. So you have many copies of the same self-attention architecture. So you ended up with, say, in this case, you get 4 heads, 4 attention heads. You get 4 sets of embeddings computed through self-attention model. Just like so, okay? Why do we do that? Because we think like, oh, well, there can be many types of relationship, right? So we should compute it in many different ways, all right? So once you have those, you concatenate the embeddings for each word and combine it like so. This is concatenation. So we're not doing anything much here. So that means embedding can be like very large then. So if the output for one attention head is an embedding of size 1000, if you do that 20 times, then you ended up with what? Embedding of size 20,000, and we don't want that. How do we change the vector, the long vector into a short vector? Multiply it by a matrix that will shrink it. So we will multiply that by a matrix that will shrink it. So you shrink it back into the previous size. So that's multi-head. Okay, so you do the same self-attention thing that many times, combining that and compress that. The real reason for multi-head, this is not on the slide, but quite important. The real reason why we do multi-head is that if one head is bad, we have other heads to rescue it, because it's quite unstable. This model is not very easy to train from scratch. So yeah, they come up with this kind of thing. So if you have like 10 heads and 2 heads are bad, you have the other 8 heads to recover. So the reason for it is not very exciting. Okay. And yeah, that's it for self-attention. And that's this innovation that changes everything, because now we get embeddings that are highly contextualized. Now you can do more things. So transformer. Transformer, it was first used for machine translation. Actually, it wasn't used for like a for a chatbot and LLM before. So it was a smaller model before that uses transformer. Then we turned it into an actual large language model, as in the model that predicts the next word. And you can see that there's much progress here. On the y-axis is perplexity, so that's the metric for measuring the quality of of language model. The lower the better. And before that we have RNN. Actually, these are all RNN of sort. When you have GPT-2, GPT-3, you can see that it got much better. GPT-2, GPT-3, they are from OpenAI when they're still a research institution, but now they are a normal software company that sell you APIs and software, which is great as well. So GPT-2, GPT-3, what I want you to notice here is that these are, we're not going to read the papers, we will read the paper titles. For GPT-2, what they really advertise it is that language models, we learn language models, right? GPT-2 is a transformer-based language model that are unsupervised multitask learners. That means it can do many tasks in an unsupervised fashion, which means we won't have to train it at all. It can do classification without training. So that's what GPT-2 is supposed to be good at. And GPT-3, though, they claim that they are few-shot learners. That means it can learn from the new data as well. Okay, so these are the innovation for GPT-2 and GPT-3. And to look at it closer, GPT-2, 2019, you are definitely born now, right? Before that, we talk about the language models before that came before you were born, but now you're definitely born. Okay, it got 1.5 billion parameters, so it's a lot. It's a lot of parameters. All right, 1,500 millions parameters. And another innovation for it is that it's actually a large language model because it's quite large. It's a big model, and it trained on a large amount of data. It's 2 billion words, scraped from all over the internet, and all the languages as well. They all get swept into this model. Although we could have trained RNN actually for in this volume, but nobody did actually, and it's still a question whether if you train RNN at this scale, what would happen. Somebody tried that. It turned out it worked okay actually. Okay, so yeah, so this is a new innovation. So like, not much on the model side, but it's more on the amount of data that they put in it. So it's a lot. It's like the biggest, the largest model we have seen. So we call it large language model. And then GPT-3, which is 1 year over, they made it even bigger. It's 200 billion parameters now. So they scaled up even more on the data, on the parameter, on the number of parameters, and also the computes, as in the training time and the training power, the computing power that they use. That's when you get GPT-3. And notice that you guys probably haven't heard of GPT-2 before, right? When ChatGPT came about, it's already GPT-3. GPT-2. Oh yeah, yes. You use GPT-2. Yeah, it's that one. It's this model. It's actually quite good. So let's look back at GPT-2. So it's not just a model that performed well on this benchmark. What it does really well is that it can do zero-shot learning. What it could do is something like this. So you can give it a prompt, but back in the day, it cannot understand very complicated prompt. So this is what the prompt means. So you give it a task description, say translate English to French, and then you give it this kind of symbol. Okay, it will try to fill in the blank for you. It's just very cute. Okay, this is what GPT-2 can do. They found it for a few tasks. I have a demo for you. Okay. Connected. So yeah, so we have used GPT-2 before to score sentences, right? And it did so much better than the small in-gram models that we have trained. Again, not really a fair comparison. You know, one model is a 5-gram language model trained on 2 million words, and the other one is trained on 200 billion words, right? It's not really a fair comparison. But yeah, but let's go. Let's wait a bit. Okay. So the size of the model actually not bad. It's only 3 gigabytes, so it can be downloaded over the internet quite easily. If you can wait 30 seconds. All right, should be easy from now. Okay, cool. So yeah, so you can make it generate text from any context you think of. In this case, I give it like some space and astronaut, going to cosmic void and all that, and it would know that this is the context of like some sci-fi movie, and give and generate something that looks much better than RNN, right? I have a strange visitor, the unicorn said. He wants, did I say, is that a unicorn in this universe? Yeah, that's a unicorn with a shimmering silver mane and a horn that pulse celestial energy. Wow, really special unicorn. So yeah, so it writes a story based on this celestial, magical unicorn thing. Leo was a bit confused. Who's Leo? Leo is this guy. Why do I point that out? Because now it knows like a long range dependency, right? To be able to repeat this name again, it needs to know that this is a character that's been mentioned before, okay? And once again, the unicorn said, the unicorn came back because we generate this thing before and we know that in the context here, that is a context of the conversation. So they'll go back and forth like this, right? And that's awesome. It has a very long range dependency. Now we know almost for sure that it can model that quite well. And this is a zero shot thing that they talk about here. So suppose I give it a really long string from some random news that I got that day. And if you put this here, this special symbol, TLDR, too long, don't read. And this will turn into a summarizer with this very simple prompt. The city of Chiang Mai has a total air population problem. Air pollution in Chiang Mai is the worst in the country. That's the summary. And it also generates precautions for you, which is, not what we asked for. So this is what they meant by zero shot. And the prompting that they're talking about is something really weird. So something that's like not so straightforward. So for example, if you wanted to summarize something, you need to know that you need to put this token right here, TLDR, and you would know that this is a summarization task. Okay? So this is what we found from GPT-2. But again, we need to prompt it to use it well, and not natural language prompt. You just have to know. And the reason how it could do this though is that in the training data, there are some articles that have TLDR in the middle and have the summary right after it. So they've seen many of these articles that have the summaries baked in. So when it saw this token TLDR, it knows that it needs to be followed by a summary, which is awesome. This is something that we didn't think it would happen actually. And do I have? Oh yeah, yes. Technical word again. This is an emerging capability because all it trains to do is to predict the next word, just like RNN, But it has like some emerging capability that that the researchers pointed out that, it can do more than just predicting the next word. It can do other tasks now. So now this is when language model become more than just what compute you the probability, which we have tried before. And it can do more than just predicting the next word, which is an assignment that you do after the midterm. It can do zero-shot learning. And we call that zero-shot because we never train it specifically to do this task. So that's why we call it zero-shot. And we call it zero-shot also because we don't perform any gradient update to instruct it to summarize something. You only have to put that TLDR thing. So we don't compute any gradient, only forward pass. All right. All right, more vocab. One shot and few shot. So in GPT-3, they found that it could learn from the patterns as well. So one shot, so you, to perform one shot translation, you train it once. So you give it one training sample. This is one shot learning. Okay, so you have to give it in a very specific way. GPT-3 is not great yet. It cannot do what ChatGPT does, right? So that's what we had to do before. And few shot learning is an extension of one shot learning. So instead of giving it just one training sample, you give a few instead of one. So we call that few shot learning. And once again, if you say few shot learning, you assume that you don't perform any gradient updates. So you don't change the parameters at all, which is so strange, right? Earlier today, when you train RNN, you have to compute all that gradient backpropagation something, right? But now it can do a new task that is unseen, and it can learn from the training data without changing anything. So this is really a revolutionary moment for NLP. And that's what we learned from GPT-2 and GPT-3. So we found that it has this few shot learning as an emerging capability. Emerging as in we didn't think it would happen, but it just emerges. Okay. Okay, I just said that, and then they found that there are patterns like this in the training data. So for example, it knows how to translate because they found data set like this. I hate the word perfume. Bird says it's somewhat better in French. There's a word French in here. Parfum. Okay? So there's some data like this that it performs translation without performing it. So from patterns like this, which might not exist a lot, but it might exist like 100,000 times, it learned that to translate is to do something that you see in this pattern. Okay? Like, if this sounds a bit of stretch, consider this question in French. As-tu allé au cinéma? Or did you go to the movies? So in this training in this training data, it kind of shows the language model how to translate from English to French, which is interesting. And the breakthrough from GPT-3 is about the scale as well. They found that scaling is key. Key as in we don't have to do anything smarter. You just need to wait. So instead of trying to come up with better models, don't do that. Well, do that too, and also give the old model a lot of data and wait a long time, and something good will come. And on in this graph, the x-axis is the number of parameters in the LLM, and y-axis is the accuracy. The higher, the better. So you can see the trend. The bigger the model, the better. We didn't see this before. At some point, for the older models, when you increase the number of parameters, let's say the number of hidden layers or the size of the embeddings, you don't see this gain anymore. But from this experimentation, they see that the accuracy should just keep going. Same for the language modeling side. Perplexity is lower the better. So you can see that if you increase the number of parameters, the perplexity keeps going down. Cool. So that's GPT-3 that we don't really get to use actually, because when GPT-3 came out in 2020, I think that's still like under Elon Musk back then. I think it was actually. It's really funny actually. So OpenAI, that's when OpenAI become closed AI. So they said that, oh, GPT-3 is so scary smart. This is what's gonna come for us. That's gonna come and take over the world. So to save the world, let me keep this model away from all of you. Let me think about ways to tame this AI monstrosity that would come and crush us, okay? So GPT-3 was never open. Oh, that's only a paper because it's so dangerous, okay? But now everybody is just using something even worse, even larger. So come ChatGPT. So OpenAI become Close AI and come up with ChatGPT, which is based on GPT-3.5 because they do something more with GPT-3, which is already large. To now that we learn quite a bit about the transformer architecture, GPT-3.5 or ChatGPT has this many parameters, 175 billion parameters, so it's too large to be run on any commercial consumer grade computer. So it has to be something expensive. And it has 96 layers. So what does it mean, 96 layers? It did the self-attention thing that I told you 96 times, okay? Do the self-attention matrix, multiply with the value vector, do layer norm, residual, feed forward, and again, 96 times. So it's a lot of parameters. It's a lot of computation to predict one word. And oh yeah, the embeddings. I always tell you embeddings in hundreds, right? The dimensions are in hundreds. No, now it's in thousands, okay? And attention heads, I told you about attention head. Why stop at one self attention per block, per layer? Do it 96 times because it's fun. And context length is the sequence length that we already talk about, right? When you train RNN, the context length is 2,000, but now Gemini claim what? 1 million, right? Context size, the sequence length, 1 million it said, and then OpenAI follows suit. GPT-5 is now like whatever 200,000. A lot, yeah, a lot. But GPT 3.5 when it first came out, it's quite a thing. The context length is actually quite small, so that means it can process 2,000 tokens at a time. But not the case anymore. Now it can do so much more. Okay, so how does it do it? Let's look at this in more detail, and this will be the last thing we talk about, I think. Yes, okay, pre-training. So pre-training, that means it trained to predict the next word, just like we train RNN like just now, but we do it at a much bigger scale. So how big and where do the data come from? It come from the internet, actually all of the internet, and filter out for some weird stuff like HTML tags or some like bad websites, whatever, like scam, gambling website. You filter out all that or bad words so that it doesn't pick up like bad behavior and so on. So it filters out quite a bit. So Common Crawl is the main source of that. So which means if the language is on the internet a lot, it will be much better represented in ChatGPT or any large language models that you use now. So a lot. Okay, so what makes it ChatGPT though? So this is a study by Google. So it gives you what you really want ChatGPT to be, and it is now, is to give it like an actual question in natural language, and it would just know what to do, right? Or if you give it multiple choice question, it should know that it's a multiple choice question, and it should give you the correct answer based on the questions given to it, right? So if you give GPT-3, but in this case you use Palm which is like GPT, but Google. I think Gemini is based on Palm, but I'm not sure because they don't tell you. All right, cool. Let's look at this. So it's a normal multiple choice question, right? So in the following sentences, explain the antecedent of the pronoun which thing the pronoun refers to, or instead it's ambiguous. The reporter and the chef will discuss their favorite dishes. Oh, okay. Whose favorite dishes? The reporter or the chef, or ambiguous? You don't know that, right? So what happened though is that if you use just GPT alone, it will give you this. It's not A or B or C at all. It's some text. Okay, so it's not a good assistant, right? So now we need a way to turn something that can just predict the next word, can know to understand some simple task description to be something really user friendly. Okay, so we are breaking away from predicting the next word now. Now we want to fold the users in to make an application. So that process is called post-training. Pre-training is we saw before. It's what we did with RNN, but with RNN we just call it training, or in n-gram model we just call it training. We don't call it pre-training. Okay, so when we say that when we say pre-training and post-training, that means we're going to do something more with it. Pre-training is just a warm-up. Okay, because it doesn't have the usefulness on its own until you post-train it. That's why we separate that now. Okay, so that's why GPT-3 are never used for computing probability of the sentence anymore. For that, we use GPT-2 or n-gram language model for that matter. All right, so post-training. So post-training, we do two things, which I would not go into too much detail, but I will tell you the process, okay? But the technicality I'll leave out. We do two things. We do instruction fine-tuning or supervised fine-tuning, and alignment with human feedback. Okay, so you might have heard, on internet, oh yeah, I have LLM, our company, our startup, fine-tune the model to match medical use, legal use, finance, education, or what have you. This is also post-training, okay? It's also called fine-tuning. So you have something that's already pre-trained, but you want to fine-tune it to your use, okay? So ChatGPT already did that, a lot, because that's how you can use it for so many things. So what all the companies are doing now, Gemini, Google, OpenAI, Anthropic, what they are all doing now is just post-training, because pre-training is done. We use all of the tokens that are available in this world. I'm not exaggerating. All of the tokens, any words that human ever typed, basically is being used now, except for, do a text over line or something. That's probably not used, but yeah. So we use a lot of these now. Now we ended up with synthetic data, you use Gemini to gen more text and use it to train another model. But yeah, forget about that thing.
You say we use all the token available in this world. So nowadays, LLM can go understand all the vocab in this world.
So the question is so now we feed everything that's on the internet onto LLM and has seen every single token. So does it mean that it understands everything in every language now? The answer is, we don't probably know. Probably no, because the model has, again, limited capacity, and it's also prefer. So since it's have the limited capacity, it will give more of the capacity to things that they have seen more frequently. So English. But to fix that though, you can use post-training to fix that so that it has, say, newer fact, or it knows more about Thai, it knows more about Indonesian. So you can do it at the post-training, as a post-training process. But what do we do? What did they do? And what are they doing now? These two things: supervised fine-tuning and alignment with human feedback. Fine tuning. So since in the normal model, in pre-training, you just give it raw text, right? And it will just predict the next word. So this is kind of boring because if you wanted to do a certain task, just train it to do those tasks. So for example, if you wanted to be able to answer questions, then you train it on this prompt and answer pairs. So this is supervised now. It's not free anymore. So you have to generate these data sets somehow, okay? All right, and I won't talk about chain of thought fine tuning, but yeah, so fine tuning, you have a bunch of these, okay? And a bunch, I mean, like, what's that? Yeah.
You said we sort of have already exhausted the training process.
Yeah.
Would it be better if we selectively choose the resource for the training process? Say textbooks?
Yeah. Yes. So the answer was why do we use all of them, all of the tokens in this way? Why don't we use like certain like specific sources more, specific languages more? The answer is yes. That's exactly what they found. To further improve the model, they pre-train more, but they use different mix of these data. And for example, Thai large language model, Typhoon, right? We love that Thai LLM. So what they did is to get some pre-trained model and train it further more on the Thai language data. So it gets much better on recognizing, on understanding Thai language. So yes, so like you can totally control the amount or things that that the models learns from. Yeah.
So when people say, let's say, like, Gemini bot, let's say it's better than ChatGPT, is it a result of this retraining or post-training for a little bit of time?
Okay, so people have some claims and beliefs that some models are better than others for certain tasks, right? Why do they differ? They do differ because of the recipe. How do you mix the pre-training data and how much you do supervised fine tuning actually? How many prompts do you use? How you frame the answer? So yes, so that's why they kind of diverge a little bit now, but I think they're kind of the same. For me, they're all the same. Okay, so do we have time? Do we have time? We can finish this. So there are actually data sets. This when the humanity kind of bonds together to train AI. So in this paper, they asked a bunch of people to contribute to the prompt and answer pair, so that you can train AI on it. So you get a bunch of people, just write the prompt that you want the AI to understand and write the example answer for that tool. So that's how you get a bunch of data and you convert sentiment analysis data into prompt and answer pair instead of text and label pair. So you convert it somehow using regular expression. You can do that too. Or actually for coding, they convert Stack Overflow onto the prompt and answer pair. You convert the comment, the doc string, and the code into the prompt and answer pair. So then there are many tricks that generate prompt and answer pair. So once you know how ChatGPT gets so good, it's just kind of, it's still amazing though, but you're just like, oh yeah, because it has seen a lot of code and has seen a lot of doc strings and has seen a lot of comments, so it knows how to write the code and yeah, and many more. So you end up with this gigantic instruction prompt answer pair data set, and you train directly on this data set. Okay, so encodes the prompt and then try to predict the answer string based on the prompt. Okay, I'll say two more things. Okay, we have time. Okay, so another amazing thing though, after they do this, there's more emerging property. So they ask, so if we give them if we give them the prompt and answer pair for all the tasks, for some tasks, are they also good at and understanding the task that they haven't seen? Do they generalize to other prompts in general? So I don't think I have the graph here. So when they test it on the task that it hasn't seen before, it can also do that quite well. It can it improve the result. So which means, so when we do instruction fine tuning or supervised fine tuning, is not just so that they have the ability to do those tasks, it's also for it to understand the prompt in general. So when it see an unseen prompt, unseen task, it can perform that too. So when we use ChatGPT, it seems like, and it can, right? It can do all things. It's because it's an emerging property from supervised fine tuning, which is amazing. And this all happens so fast too.
Do we know what's the mechanism behind it? As in, like, eventually it breaks down to back to math, right?
Do we know the mechanism? No. Even the Transformers themselves, we don't know the mechanism. So we lost basically all the ability to understand the model that we use now because it's so large. Yeah.
Ever since we use Tranformers, so it's been a black box.
It's a black box, but it's like a research area where people to try to find ways to understand what's happening inside. Yeah.
So it is basically like alien technologies right now.
It's basically alien technology right now. It's more or less. It's more or less. No, we know something about it. Yeah. Okay. Last thing then, before we go. Besides besides giving like a direct prompt and answer pairs, another thing that ChatGPT was done on was to model to maximize the preference of the user, because sometimes we also want the LLM to be able to give the answer that user like, which might be different than the correct answer. Usually the correct answer, there's only one. For some questions you don't have the definite answer, right? But there's the style answer that the user like. So to fine tune the style, it's not about doing the task right anymore. It's about the style of how to answer, like use bullet points, or put the summary at the end, or start with yes, great, I like that answer. The style you use the user preference user preference to train the model. So what's happening before ChatGPT become ChatGPT is that it uses the model to respond to a prompt and ask for 4 different ways of responding to it, and get people to rank it from best to worst. And from this data, so the user didn't have to tell them why or what the right answer should be. They only have to rank it, and from ranking, it optimizes for the preference. So the response get better as in it matches the user's style. Okay, so it's not about like, oh, does it translate correctly? Does it summarize well? It's about, does it summarize to the style that the user like? Okay. So you can see now why ChatGPT like giving you like a bullet point style answer, because it's probably from this process. So the user like that kind of answer as opposed to like a long article, a long essay. Okay, so once you have this kind of preference data, you fine tune the model even more so that it's aligned with the human preference. And once you do that, you can see that people prefer the response from the model that's human preference aligned more. Yeah, and that's Transformer. So it goes way beyond what we saw before in Ngram, where we use language model just to score and to fill in the blank, just in a shorter context. Now from predicting the next word, now you have an all-around NLP tool that can do classification, it can do sequence-to-sequence tasks, it can do summarization, machine translation, and what have you. So this is due to the emerging property of it. Okay, so now we get to ChatGPT and how it came about without much math. And next week we'll look back on how to use transformer-based model to use it as a classifier. All right. See you next week. Yes.